this module, Module 16, we're going to talk about delays of digital circuits. And particularly, we're going to talk about how long does it take for an input change to cause a corresponding output change. And those delays can be either a minimum delay or a maximum delay. We'll talk about why it can have either a minimum or maximum delay in this module as well. We'll also talk about hazards, where an input change causes multiple output changes. So let's first talk about timing. So again, timing refers to measuring how long it takes, or the delay between an input change causing an output to change. So if A, for example, transitions from 0 to 1, here's our 0 to 1 transition. This is called a timing waveform. Here's our 0 level and our 1 level. So if A changes from 0 to 1 in this buffer, A goes from 0 to 1, well, Y we know is going to go from 0 to 1 as well, but it may take some time. This delay, this difference between the time where the input changes A and to when the output changes is called delay. And so we can break this delay down even further and talk about minimum delay and maximum delay. The maximum delay from an input changing to the output changing is called the propagation delay, or the way we write it, TPD. We also have a minimum delay, and we call that the contamination delay, or TCD. So let's look at how that looks on a timing waveform. So here we have A transitioning either from 0 to 1 or from 1 to 0. So those two lines indicate that it doesn't matter which transition it is, it's either 0 to 1 or 1 to 0. And now we look at the output, Y. It could transition, again, from either 0 to 1 or 1 to 0. The earliest it could transition from the input transitioning is the contamination delay, TCD. And then these hash lines indicate that the output can transition even multiple times within that. But the maximum delay is, again, the delay between the input changing and the output settling to either 0 or 1. So that's the maximum delay, or the propagation delay. So we call contamination delay contamination because the output at this point is contaminated. It's no longer a clean signal of either 1 or 0. It's now changing and transitioning. And so we call the signal has been contaminated at that point. So the contamination delay, the earliest point at which it could start changing, and propagation delay is the maximum delay, or the point at which the output stops changing. It settles to either 1 or 0. So what is delay caused by? Well, it can be caused by capacitance and resistance in a circuit. Totally fine if you don't know what those words mean. If you take E220, you'll start to know what those mean. But basically, capacitance is how much capacity it has to hold charges. And resistance is how much a circuit resists the flow of current. And the largest limit, the boundary, is the speed of light limitation. So the fastest that an electrical signal can travel is the speed of light. Okay, so now the question is, why are the minimum and maximum delays different? Why do we have differences between TPD, again, the propagation delay or the maximum delay of a circuit, and TCD, contamination delay, the minimum delay of a circuit? Well, we could have a circuit with different rising and falling delays. So a circuit making the output rise from 0 to 1. That delay could be faster or slower than making the output fall from 1 to 0. Our circuits also have multiple inputs and multiple outputs. Some paths between those inputs and outputs are faster than others, and some are slower. I'll show examples of those as well. And then there are physical reasons why TPD and TCD may be different. Well, circuits slow down when they get hot, and they speed up when they're cold. So a circuit has to operate within a range of temperatures, and that specification is given on what's called the data sheet of a circuit. And so you look at that data sheet and it may say, hey, it can operate between minus 5 degrees Celsius and, whatever, 100 degrees Celsius or something. And so that circuit across that range will have a minimum delay and a maximum delay. When it's in the coldest temperature range, the minus 5 degrees Celsius, then it's going to be faster than when it's in the hotter temperature range, the 100 degrees Celsius. It will then be slower. Okay, so there are different reasons why we have a minimum and maximum delay of a circuit, and they range from being physical reasons of actually, temperature variation, overall the speed of light, as well as other factors such as capacitance, resistance, different paths in the circuit, and so forth. So here's an example circuit. We can analyze the paths between the input and the output. So here's a long path or a critical path of that circuit between either A or B and the output Y. That's called the critical path or the long path. And then we also have a short path here, which is our path from D, the input D, to the output Y, and that's our short path. And so we have, if we have a black box and we look at A, B, C, D, and the output Y, there's our interface, our inputs and our outputs. And we want to know, well, what's the maximum delay of this circuit and what's the minimum delay? Well, the maximum delay is going to be determined by the critical or the long path. So in this case, we have an AND gate delay plus an OR gate delay plus an AND gate delay. So we have two propagation delays or maximum delays of AND gates plus a single OR gate delay. For the short path, we use the minimum delays of each circuit element, in this case of each gate. So we're going to use, the short path for this circuit is just the single delay of an AND gate. And again, we use the minimum delay for that gate because we want to look for the minimum time from an input changing to the output changing. So for example, we could give numbers to this. Suppose our AND gate, the maximum delay is 30 picoseconds or something. So TPD AND is 30 picoseconds. And propagation delay of the OR gate, the maximum delay of an OR gate could be, for example, 20 picoseconds. So then the overall critical path or TPD maximum delay of the circuit is then 2 times 30, we get 60 picoseconds plus 20 picoseconds. So the overall delay of that circuit is then 80 picoseconds. For our short path, we then take the minimum delay of our AND gate, TCD and let's suppose that minimum delay is 10 picoseconds. So then the minimum delay of our circuit overall, TCD, is just equal to 10 picoseconds. So when I look at this overall circuit, I'm guaranteed that the earliest time that the output will change, given an input change, would be 10 picoseconds later. And the maximum delay between an input changing and the output changing is then 80 picoseconds. So now I have a timing specification for this circuit as well. So a question may be, well, where did we get these numbers from? These individual minimum and maximum delays for the gates. Well, those are taken from data sheets. So I can look up what gate I'm using and it will give me a minimum and maximum delay. And eventually those are derived from Well, what we talked about in one of the prior slides, speed of light, resistance and capacitance, temperature ranges, and so forth. So now let's talk about the last topic of this module, which is hazards. These are also called glitches. A glitch occurs when a single input change causes an output to change multiple times. So let's examine a circuit and see how this works. So here's a circuit that we have, and we could figure out what the equation is. In fact, it's A bar and B bar, A bar and B bar, or B and C. So here's our equation, A bar and B bar, or B and C. Also put that into a K-map to see what that looks like. So we have this circuit, and let's suppose that we have A equals 0, and C equals 1, and B falls. That means B starts out at 1, and then it's going to transition to 0. So first of all, let's see how this circuit evaluates. Well, we can even just look at the equation and say, well, we do have B and C, so we know that the output's going to be true. And we can observe that from the circuit as well. B and C, this one is true. We get something, or 1. Turns out that this node is A bar, which is 1, and B bar, which is 0. So that's going to be a 0. But because of this 1 here, we get Y equals 1. And now we want to see what happens when B transitions from 1 to 0, when B falls. So B is going from 1 to 0. And we look at this path here, and that's just a wire, so there's no delay there. So this, now we have a 0 on this side of our AND gate, on this input of the AND gate. We get 0 and 1. So this output of that AND gate transitions to 0. And now we have 0 or 0 on the input of our OR gate. And so our output transitions to 0. But sometime later, this inverter here transitions from, well, its input transitioned from 1 to 0, so its output transitions from 0 to 1. But it takes some time. That inverter has some delay. And so now we get a 1 and a 1 on the input of our AND gate, and that causes our output to transition to 1. 1 and 1 equals 1. And now our OR gate has a 1 or 0 on its input, and its output now transitions back to 1. We expect, because of this term, A bar, B bar, we expect the output to be true. But in fact, we got the output transitioning, because of delay, from 1 to 0 and back to 1. So that output transitioned multiple times, in this case twice, 1 to 0, that's one transition, from 0 to 1. And if we saw this on an oscilloscope, we put a probe on our wire here, on Y, we might say, that's not at all how I expected that to work. I expected it to stay at 1. But if we understand underlying this are delays of circuits, particularly the longer path, because of this inverter here, cause that top path to be slower, this path here, to be slower than this bottom path. And so it caused our output to change multiple times. And here we show it in a timing waveform. Again, this is our timing waveform where we have time on the x-axis. And here we have our different variables, our inputs and outputs. And we have the 1 level and the 0 level for each of those. So B transitions from high to low, from 1 to 0. So B falls. And sometime later, it causes N2, this internal node, N2, to fall, just like we saw. So now we have a 0 and 1. on the input of that AND gate. And that transition causes Y, because now we have a 0 or 0 on the input of our OR gate, causes the output to transition to 0 momentarily until the top path catches up and we get our N1 node rising to 1, because now we have a 0 bar 1 and 0 bar 1, and we finally get that transition to 1 here. Now we have a 1 or a 0, and it pulls Y back up to 1. So we can see it on our timing diagram as well. So, well, first of all, why is this important? Well, it's important to know in either simulation or in practice with an oscilloscope. We may see this in our digital circuits. We may expect logically this output value should be 1 the entire time. Right, we have A bar and B bar, or B and C. Well, when we have A, B, C equals, well, it started out as 0, 1, 1, and it transitioned to A, B, C being 0, 0, 1. Well, B and C is true in the first case. A bar, B bar is true in the second case. So either of those logically evaluate to 1. We expect our output to remain at 1. But because of physical delays in the circuit, it glitches down momentarily to 0. So in this case, we can fix the glitch. But let me emphasize that this is not the point of this discussion about glitches, also called hazards. The main point of this discussion about glitches and hazards is that, number one, they occur because of delay. And so if you observe them in simulation or on an oscilloscope, this is what's happening. You know where they're coming from. We can sometimes fix the glitch, which we're going to do now, but usually we don't. And the reason we don't is because we basically ignore it. We say, hey, you know what? I'm not even going to look at that signal until it's stable. And we do that using sequential logic, which we'll start talking about in chapter 3. Okay, but for now we're going to, quote, fix this glitch. But again, this is kind of a side, this is the lesser significant bit of this discussion. So we can fix this glitch by basically introducing this term here. So what happened is we transitioned between these two product terms that were causing the output to be 1. During that transition between product terms, they were momentarily both 0 until we finally transitioned completely over to the second product term, in this case the A bar, B bar term. But if we introduce a term that overlaps those two product terms, so in this case the A bar C term, we can get rid of this glitch. If you recall, this A bar C term is the consensus term. So we have the true form of B ANDed with something, or the complement form of B ANDed with something. And then we AND those two somethings together to get our consensus term. So we introduce this consensus term here, physically as an AND gate that takes A bar and C. We notice this term, when B transitions from 1 to 0, the entire time A bar and C, well, let's see, A bar is 0, so A bar is 1, C is 1, we get 1 and 1. That causes the output Y to be 1, even as B transitions from 1 to 0. So in this case, we fix the glitch again by adding a term that overlaps two product terms that are adjacent but non-overlapping. But the main point of glitches and hazards is to understand that they occur, first of all. So to recognize them, especially in simulations or in oscilloscope. And then to realize, hey, I need to make sure that I don't try to look at the signal while it's transitioning. And we can do that by introducing what's called synchronous design. And we'll talk about that in chapter 3. Which basically, synchronous design, think of synchronicity, or synchronous. It's synchronous to a clock that says tick, 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 and only at the ticks do we, or to specify time, do we actually even look at the signals. And we set up that timing so that it's long enough that these glitches can occur and then the signal can stabilize before we even look at the signal. And again, we can't get rid of all glitches. For example, simultaneous transitions on multiple inputs can also cause glitches. So that last part where we're getting rid of the glitch is interesting, but not the main point.